We just showed that we could combine a two-port device with a load attached to it and interpret it as a impedance transformer, one that transforms load impedance into a new impedance Zn. We combine the two-port device and the load attached to it. And of course that allowed us to determine the voltage and current at the input of that two-port device. Let's say we have a different situation now. Instead of combining these two things together to determine the voltage and current at port 2, let's say we're interested at port 1, that should be V1 there. Let's say we're interested in the voltage and current here at port 2. How would we do that analysis? Well, one thing we could do there is a similar kind of procedure. We draw a line right here at the output port of our two-port device between the two-port device and the load. And we say, all right, everything to the right is an equivalent circuit. Of course, we already know what that is. That's ZL. That is the equivalent circuit to everything to the right. And then we're going to come up with an equivalent circuit then to everything to the left. To the left of this port plane, we have two devices. We have our Thevens equivalent, original Thevens equivalent, and we have our two-port device. And so now we're going to combine those two things together. Instead of thinking about attaching a load to a two-port device and transforming it into a new one-port device with a input impedance of with a new input impedance rather, what we're going to do is think about it as taking a source and connecting a two-port device to it, and that will transform the original source now into a new source, one that we can use to evaluate the voltage and current at the at this second port I1 and V2. So here is our new problem. Again, we're going to cut our circuit into two pieces right now at this port plane where we define voltage 2 and I2 here, and we're going to combine everything to the left into a new equivalent circuit. What is the equivalent circuit to everything looking to the left here? Well, remember, this source is supplying energy at a certain rate, so we need to come up with a Thevens equivalent of this entire circuit. How do we come up with the Thevens equivalent of this circuit? Well, it's the same procedure for any and all circuits. If I want to determine the Thevens equivalent, I need to determine the open circuit voltage at this port plane and likewise the short circuit current. Once we determine those two things, we have everything we need to determine the Thevens equivalent or the Norton's equivalent if we're so inclined. So we connect a short circuit here to port 2, and we define a short circuit current. In this case, we define short circuit current as positive when coming out of the port, and so through the short circuit from top to bottom. And that's important that we define positive current in that way so we'll get the right result for a Thevens equivalent. And so we're trying to figure out what is this current, and notice this current will be simply the opposite of whatever I2 is. We simply need to solve therefore for I2 and multiply it by -1. How do we determine I2? Well, we've done this before. We have an equation now for our source, all right? It's right there. We have an equation for our load. In this case, we put a short circuit at the end of this two-port device, and that means that V2 is equal to 0. That is the device equation for a short circuit, after all. And then we have the two equations for the two-port device using the transimpedance parameters. And so we have 4 equations and 4 unknowns, and we can use these 4 equations to determine the value of I2. I say 4 unknowns, actually. We know V2 is equal to 0, so there's really 3 unknowns. Let's solve for I2 and then multiply by -1, and that will give us the short circuit current. We do the algebra and we come up with the answer then for I2 multiplied by -1. That gives us our short circuit current. And we look at this result and it passes all of our sanity checks. First of all, this is a complex number and this is a complex number. It has the right units on the right side, and of course that is units of ohms. And likewise, when we go through and look at every parameter in the result, it is all the parameters that are used to describe our circuit, VG, ZG, and the 4 transimpedance parameters. So it seems to pass our sanity check. When we're done finding the short circuit current, we need to move on to the open circuit voltage at the output port, at port 2. We find it pretty much the same as we did the short circuit current. Really, the only difference here is we changed the device equation for the equation attached to this output port. Before we had a short circuit, which said that V2 is equal to 0. Now we have an open circuit, and that device equation is I2 equal to 0. So of the four equations, we changed the one that says V2 equal to 0 to I2 equal to 0. Otherwise, the procedure is the same. We go through and solve now for V2, and that is our open circuit voltage. Doing the algebra, we find this is the result. In this case, we find the complex number on the left and complex number on the right. We find the units work out, the dimensional analysis works out. Now, in this case, this is one of those rare exceptions where the result does not involve all of the parameters in the circuit. Notice this result does not depend on Z22, nor does it depend on Z12. Now, this gives us pause, of course, and we wonder and we worry that perhaps we've done something incorrect. But in this case, I can assure you this is the right answer. Again, sometimes it turns out that the result doesn't necessarily involve all the parameters, but usually it does. This is a rare exception. So to determine the Thevens equivalent, we have all the values we need. First of all, we know the voltage source of the Thevens equivalent is equal to the open circuit voltage. In other words, it's equal to this. The source impedance for the Thevens equivalent is equal to the ratio of the open circuit voltage to the short circuit current. And when we do the algebra, we get this result here. And so this is the procedure for finding the Thevens equivalent. Many times in this class, we have to go through and come up with the Thevens equivalent to a circuit. We're going to take a port plane and look to the left from which energy is coming, and we're going to say, all right, what is the, look to the left rather, from your left, where is the energy coming, and we're going to replace all that with its equivalent circuit, in this case, the Thevens equivalent. The procedure is always exactly the same. You determine the short circuit current, the open circuit voltage, and from that you can determine the Thevens equivalent source or the Norton's source if you're so interested. There isn't any situation where you don't do those two things: short circuit current, open circuit voltage. I emphasize this because students struggle oftentimes to come up with the Thevens equivalent. We see all kinds of different methods and ways and attempts at trying to find the Thevens equivalent. And again, there's only one way. There's only one way you can find the Thevens equivalent. Determine the short circuit current, determine the open circuit voltage. If you're not doing those two things, you cannot get the right answer. Again, frequently in this class, we have to come up with that equivalent circuit. So get used to determining the short circuit current and the open circuit voltage. This procedure we're going to interpret in a very important way, and that is we're going to interpret this as a source transformation. If we look at our original circuit, we had a source that was connected to our two-port device, the one where we know the trans impedance parameters, the impedance matrix of that two-port device. And we're combining those two things into one equivalent circuit, and that equivalent circuit, of course, is the Thevens equivalent. One way to view this is I took an original source and I connected a two-port device to it on its output, and we have transformed an original source into a new source. We have changed the values of that Thevens equivalent. We've changed not only the source impedance ZG into Z out, done that impedance transformation, we've likewise changed VG into a new voltage source V out. Both of the source and impedance values have changed. These are the parameters that describe then that transformation. ZG turns into Z out by this transformation. VG turns into V out by this transformation. Notice again, V out and Z out are both transformed from ZG and VG there. This is important with respect to when we talked about the optimal power transfer. And remember, we had a question where we said, what if we change just the source impedance? What would we do to try to maximize the power transfer? And at the time I said, even though the answer we get is correct, it's a little bit of an academic problem because it's very difficult to go through and change the source of an impedance in a useful way without, source impedance impedance of a source in a useful way without likewise changing that voltage. And that shows here. We've gone through and we've taken a two-port device and put it in front of a original source to transform it to a new one, and we have transformed the source impedance, but likewise we've transformed the voltage as well. Remember, the available power of any source depends on both its voltage source and its impedance. What we're going to find is that this transformation from one source to a new source is constrained oftentimes by that available power. We'd like to just plunk a two-port device in front of this source and increase the available power of the transformed source, but that's much easier said than done. In fact, we'll find that we can only increase the available power of a source in this transformation if this two-port device is an active device, essentially an amplifier. Otherwise, this transformation is constrained by the available power. We can't increase it if this two-port device is not an active device. So we'll go back to our first original circuit here, where we take a two-port device that we're interested in. We're wanting to understand its behavior in a system, specifically the signal at the input and the signal at the output and how they are related to each other. We showed that if we knew the equivalent circuit to everything on the left and the equivalent circuit to everything on the right, the source and the load, we could analyze this and come up with the currents and voltage simultaneously, a coupled solution that was rather complex. But then we've showed that perhaps the easier way of do that is to break the problem into two pieces. Find what's going on at port 1 and then find out what's going on at port 2. To determine what's going on in port 1, we combine the right side of port 1, everything here, into one equivalent one-port device. And we interpret that combining of the two-port device and the original ZL as an impedance transformation. We say the two-port device transforms ZL into a new input impedance, which is the equivalent for everything to the right of this port plane. And once we have that new input impedance, then we have a very simple source connected to load, and we can determine current, voltage, power, and so forth. Moreover, I've stated that the transformation that is completed from ZL into a new value Zn will tell us something about that two-port device, and we'll get to those that result later, what it tells us. But it's a very important aspect in microwave engineering, radio engineering, this idea of an impedance transformation. How does a two-port device transform a load attached to it into a new impedance, which is the input equivalent of the entire circuit? Likewise, if we go through and we want to understand what's happening at port 2 at the output of our two-port device, the input to our load, we want to find I2 and V2, we could go through and again use our coupled solutions or clunky coupled solutions, or we could go through and say, let's draw a line in the circuit right here, divide the port plane. Everything to the right is an equivalent circuit. Well, that's just ZL. Now let's take everything to the left and combine it into one equivalent circuit. It's Thevens equivalent, and we have that here. Once again, it's important to interpret this step of going from this to this as a source transformation. We look at it as if this two-port device transforms this original source into a new source. We put a source and connect a two-port device to it, and now we have a new source transformed by that two-port device. If we know V out and Z out and ZL, of course, we can determine I2 and V2 and the power and everything and find out what's going on at the output here. But in addition to that, this transformation that occurs will likewise tell us something about this two-port device, what it does, how it's useful, and what its characteristics are. So once we transform our original source into a new source, again, we simply cut the circuit into two pieces here and replace it with equivalent circuit in the left and right. Now we're back to our original source connected to load, and it's simply evaluated with Ohm's law and voltage division for V2 and I2, and we get that result here very quickly. In this case, though, in terms of the transformed source, so it's in terms of V out and Z out. From that, of course, we can determine then the rate of power flow across that the rate of energy flow rather across this interface, the power that we have out of and we say sometimes people say it's out of the two-port device. Again, it's really out of everything to the left. What's coming out of everything to the left is what's being delivered by that now is absorbed by this load. That's the rate of energy flow across this plane, and that's the absorbed power by ZL. And of course, we can determine that if we know what I2 and V2 are, then this gives us the result. Sandy check time. This is a real value. These are all real values. This has units of power. This has units of power. This result uses all of the parameters of our circuit: V out, Z out, and ZL. So that looks like a good result, and it is the correct result. Just like the impedance transformation, this idea of a source transformation to determine the voltage occurred in port 2 causes a little stress for students, because I first provide you with that coupled solution for I1 and V2 that involved sort of that long complex equation with all of the impedances in the circuit. And then we come up in the previous page, actually right here, a value of I2 and V2, which is much simpler. But they're simpler because we've introduced the concept of a transformed source, V out and Z out, which of course depends on all of the circuit to the left of that port plane. Students again stress because they worry about which of these two results should we use. Should we use this rather simpler form for I2 and V2, or the more complex form that I showed earlier? I want to prove here that they're exactly the same form, and so you don't need to worry about choosing the right one. If we take the value V out and Z out and we insert it in these two equations and do a little algebra, what we come up with is precisely the same result as we initially had for I2 and V2. These are the ugly equations that we came up with originally. Again, in this class, really what we always want to do is come up with a source transform and an equivalent source, and then do our algebra. Not only is it easier, I think, once again, I think the transformed source will tell us more physically about what's going on in our circuit and what our two-port device does. So I write these equations here for completeness and to show you that our transimpedance parameters for our two-port device and our equivalent circuits are sufficient for finding these currents or voltages, but I don't really ever want you to use these equations. There's no reason why you'd ever use these equations to find a value for current or voltage or power. These are the ones that I think in almost every case are the most simpler and more insightful way to get those results.